Welcome to our channel. We are so glad you found your way here. Let us help you fall asleep. Let's begin with Earth's drifting poles, why the magnetic field is moving. Take a slow, deep breath in and release it. Let the weight of the day fade away as we embark on an unhurried, atmospheric journey through the wonders of the cosmos. Your mind is quiet, the universe is vast, and we are ready to explore. Earth's magnetic field acts as a protective shield, extending into space and safeguarding the planet from solar wind and cosmic radiation generated by the movement of molten iron and nickel within its outer core. This magnetic phenomenon creates a dynamic and fluctuating environment. The field is not static, it experiences continuous changes, both in strength and structure, revealing a complex interplay of geophysical processes. The core's fluid motion generates electrical currents, which in turn produce magnetic fields. This dynamo effect results in a magnetic field that resembles a bar magnet tilted at an angle. The field lines extend from the magnetic north to south poles, forming a protective bubble known as the magnetosphere. Within this region, charged particles are deflected, preventing harmful radiation from penetrating the atmosphere. Over time, the magnetic poles have shifted, sometimes dramatically, reflecting the underlying dynamics of the Earth's interior. The current drift observed in recent decades indicates a movement toward Russia, posing questions about the stability of the field. These shifts have implications for navigation systems and animal migration patterns, as many species rely on the magnetic field for orientation. Understanding the intricacies of Earth's magnetic field offers insights into its geological history and ongoing changes, revealing the complex relationship between the planet and its environment. Scientific inquiry into Earth's magnetic field has evolved over centuries. Beginning with early observations by ancient civilizations, knowledge was initially rudimentary, often interwoven with mythology and superstitions. The first significant strides occurred during the Renaissance, when magnetic compasses began to gain prominence in navigations. This marked a pivotal shift, as explorers relied on these instruments to traverse uncharted waters. During the 17th century, William Gilbert, often regarded as the father of magnetism, published De Magnete. His work laid the groundwork for understanding magnetic forces, proposing that Earth itself behaved like a large magnet. Subsequent advancements in the 18th century, including the development of theodolites, allowed for more precise measurements and mapping of magnetic variations across different regions. In the 19th century, the study of geomagnetism expanded further, particularly through the efforts of scientists such as Carl Friedrich Gauss. His innovative techniques in data collection and analysis illuminated the complexities of Earth's magnetic field. The advent of technology in the 20th century, including satellite systems, provided an unprecedented view of magnetic field dynamics, leading to the discovery of geomagnetic reversals and fluctuations. These historical milestones underscore the continuous quest for knowledge, revealing how human understanding has gradually aligned with the intricate workings of the planet's magnetic domain. Each revelation contributes to a broader comprehension of Earth and its myriad interactions. The structure of Earth's core reveals a complex interplay of materials and dynamics. Composed primarily of iron and nickel, this innermost layer exhibits both solid and liquid states. The outer core, which surrounds the solid inner core, remains in a molten state, generating convective currents that play a crucial role in the creation of Earth's magnetic field. Temperatures within this region can exceed 5,000 degrees Celsius, creating an environment where pressures reach over 3 million times that of the surface. These extreme conditions facilitate the movement of molten iron, which, through its flow, contributes to the dynamo effect that sustains the planet's magnetic properties. As the molten material circulates, disturbances and variations in density can lead to fluctuations in magnetic intensity. This phenomenon influences not only the immediate environment, but also the dynamics of the atmosphere. The interaction between the magnetic field and solar winds leads to phenomena such as auroras, visible near the polar regions. Understanding the dynamics of this core structure is essential for comprehending both geomagnetic reversals and long-term changes in Earth's magnetic orientation. It serves as a reminder of the planet's ever-evolving nature and the intricate systems that govern its stability and behavior. Observations of these processes continue to deepen insight into Earth's fundamental workings. The geodynamo effect serves as the engine behind Earth's magnetic field. This phenomenon arises from the movement of molten iron and nickel within the outer core, where convection currents are driven by heat from the inner core and the cooling of the outer layers. The flow of conductive materials generates electric currents, which in turn produce magnetic fields. As these magnetic fields combine, they create a coherent and dynamic magnetic environment that envelops the planet. The interaction of these currents is influenced by Earth's rotation, imparting a spiral motion that organizes the magnetic field lines. This self-sustaining cycle ensures that the magnetic field remains stable over geological timescales, though it is not immune to fluctuations. Variations in temperature and pressure contribute to complex behaviors, leading to occasional polarity reversals, where the magnetic north and south switch places. The implications of the geodynamo extend beyond magnetism. It plays a crucial role in protecting the atmosphere from solar winds and cosmic radiation. This shielding is essential for maintaining conditions conducive to life. As the dynamics of the outer core evolve, the magnetic field continues to respond, reflecting changes in the subterranean processes. Such interactions highlight the intricate relationship between planetary mechanics and the enduring magnetic presence that blankets the surface, influencing both navigation and biological systems. Defining magnetic poles provides insight into their significance. These regions, where magnetic field lines converge, are crucial for understanding Earth's magnetic field dynamics. The north and south magnetic poles serve as pivotal reference points for navigation, guiding explorers and modern technology alike. Over time, these poles have shifted, revealing the fluid nature of magnetic forces and Earth's interior processes. The importance of these poles extends beyond navigation. They influence phenomena such as auroras, which arise when charged particles from the sun collide with the magnetic field. This interaction results in vibrant displays that manifest in polar regions, showcasing the beauty of electromagnetic interactions in our atmosphere. Their movement also serves as a barometer for geological activity beneath the crust. Changes in the magnetic poles can reflect shifts in the molten iron and nickel that comprise the outer core. This liquid layer generates the magnetic field through convection currents driven by heat and rotation. The ongoing drift of the magnetic poles prompts further research into its implications for climate, technology, and even migratory patterns of numerous species. Understanding these shifts supports a broader context of Earth's changing environment. The relationship between magnetic field dynamics and the planet's evolution encapsulates essential aspects of terrestrial and extraterrestrial studies. Magnetic declination and inclination are critical concepts that describe the orientation of Earth's magnetic field in relation to its surface. Declination refers to the angle between magnetic north and true north, varying significantly depending on geographic location. This angle can range from 0 to several degrees, causing navigational discrepancies and influencing the accuracy of compasses. Understanding this deviation is essential for accurate navigation and has implications for various scientific fields, from geology to atmospheric sciences. Inclination, on the other hand, signifies the angle at which magnetic field lines enter or exit the Earth's surface. This angle varies from 0 degrees at the magnetic equator to 90 degrees at the magnetic poles. The inclination provides insights into the vertical orientation of the magnetic field and helps scientists identify historical shifts in the planet's magnetic behavior. Both declination and inclination are influenced by the ongoing movement of the magnetic poles, which gradually alters the magnetic landscape of the Earth. Tracking these changes requires precise measurements and sophisticated modeling techniques. These variations are not merely academic, they can affect communications, satellite operations, and even the behavior of migratory species that rely on magnetic cues for navigation. In understanding these concepts, the intricate relationship between Earth's magnetic field and its dynamic processes becomes more apparent. Historical records indicate that the movements of the magnetic poles are not a recent phenomenon. Ancient navigators relied on the stability of magnetic orientation, yet fluctuations have been documented for centuries. Early observations revealed that these shifts occurred irregularly, with evidence of significant migrations. The pole's movement, once measured in several degrees per century, has accelerated in recent decades. Data from the last century illustrates that the North Magnetic Pole has drifted from approximately 73 degrees north latitude to more than 80 degrees north, a journey of over 2,000 kilometers. This motion is largely attributed to the dynamics within the outer core, where molten iron circulates, creating the magnetic field. This region's fluid dynamics are influenced by convection processes, resulting in changes that reverberate throughout the magnetic field. Observations have also shown that the South Magnetic Pole is not static, displaying similar tendencies of migration. The interplay between the shifting poles and geomagnetic reversals, where the magnetic field flips, adds complexity to this topic. Historical records of these reversals suggest that they occur irregularly, approximately every 250,000 years, although the interval can vary significantly. Understanding the historical context provides insight into the ongoing changes and their implications for navigation, wildlife behavior, and even climate patterns. The exploration of this phenomenon continues to reveal the profound impacts of Earth's internal processes on its magnetic field. The current rate of magnetic pole movement illustrates a dynamic and shifting landscape. Over the past century, the magnetic North Pole has been moving at an average speed of approximately 30 to 40 kilometers per year, accelerating from earlier rates. This northward drift is largely influenced by convection currents within the molten outer core, where the movement of iron and nickel generates the planet's magnetic field. In this region, changes in temperature and density create complex flow patterns that contribute to the repositioning of magnetic forces. The anomalous regions, where magnetic anomalies coexist, further complicate the magnetic field's stability. Fluctuations in these areas can impact navigation systems, leading to adjustments in maps and GPS technologies. Continual monitoring of the magnetic field reveals fluctuations in its intensity, with certain areas experiencing a weakening effect. This has implications for satellite communications and power systems, as the magnetic field provides protection from cosmic radiations. Scientific observations indicate that the South Magnetic Pole is also shifting, albeit at a different pace, moving towards the coast of Antarctica. Understanding these changes offers insights into the long-term behavior of Earth's magnetic field and its role in protecting the planet from solar winds and radiation. The interaction between these forces shapes a complex, ever-evolving magnetosphere, essential for the stability of life on Earth. The rotation of Earth plays a pivotal role in the dynamics of its magnetic field. As the planet spins on its axis, this motion influences the movement of molten iron within the outer core, The Coriolis effect results from this rotation, causing the fluid motion of these conductive materials to spiral. This spiraling motion generates electric currents, which in turn create magnetic fields. The alignment and intensity of these fields are significantly affected by the speed of Earth's rotation. Variations in rotation speed can lead to fluctuations in the generated magnetic field strength. When considering historical data, periods of increased volcanic activity and tectonic shifts correspond with alterations in rotational dynamics, potentially influencing the magnetic field's behavior. The intricate relationship between the planet's rotation and the flow of molten iron results in a constantly shifting magnetic signature. Localized anomalies can emerge as a result of this interaction, leading to areas of intensified magnetic activity. These anomalies can impact navigation systems, satellite operations, and even animal migration patterns, illustrating the interconnectedness of Earth's systems. The gradual drift of magnetic poles reflects ongoing shifts in liquid metal dynamics beneath the surface, highlighting a natural process that is both complex and essential. Understanding this relationship fosters deeper insights into planetary behavior and the stability of Earth's environment. Solar activity exerts significant influence over Earth's magnetic field, intertwining their behaviors in a complex relationship. Variations in solar output, marked by phenomena such as solar flares and coronal mass ejections, affect the magnetosphere, the protective bubble surrounding the planet. These solar events introduce charged particles that interact with the magnetic field, leading to observable changes in its structure. The solar cycle, an approximate 11-year rhythm, determines the intensity and frequency of solar phenomena. During periods of heightened solar activity, the magnetic field experiences disturbances, often causing geomagnetic storms. These storms can disrupt communication systems and impact satellites. The interaction illustrates the vulnerability of Earth's magnetic environment to external forces. In regions where this magnetic field is weaker, such as the poles, the effects of solar activity can be more pronounced. The influx of solar particles can lead to spectacular auroras, vividly demonstrating the dynamic interaction between solar wind and the planet's magnetic shield. This interplay is essential for understanding not only terrestrial phenomena, but also broader astrophysical processes. It reveals how external factors shape the magnetic landscape, offering insights into the long-term evolution of Earth and its capacity to sustain life amidst varying cosmic conditions. Each interaction serves as a reminder of the delicate balance that governs planetary systems. The intricate relationship between solar flares and the magnetic field manifests through various phenomena. As these powerful bursts of radiation erupt from the sun, they release high-energy particles that traverse the solar system. Upon reaching Earth, they interact with its magnetic field, resulting in disturbances that can reshape its configuration. These disturbances are often felt as geomagnetic storms, which can significantly impact technological systems and natural processes. This region surrounding the planet, known as the magnetosphere, acts as a protective shield. Solar flares, however, can induce currents within this shield, leading to fluctuations that may weaken its integrity. The resulting geomagnetic activity can create beautiful auroras in the polar regions, illuminating the night sky with vibrant colors. Yet, these visual spectacles come at a cost, as disruptions can also affect satellites, power grids, and communication systems. The movement of the magnetic poles, influenced by solar activity, alters the dynamics of Earth's magnetic field. Over time, shifts can lead to changes in navigation systems, as compasses align themselves with the evolving magnetic landscape. Understanding these interactions provides insight into not only the behavior of the magnetic field, but also the broader implications for the atmosphere and technological infrastructure. Each solar flare triggers a cascade of events, revealing the complex interdependencies of solar and terrestrial forces. The interplay between climate change and Earth's magnetic field is subtle yet significant. Alterations in atmospheric conditions can impact the distribution of mass within the planet. Melting ice caps and shifting ocean currents contribute to changes in gravitational pull, which may influence the magnetic field's stability. This region of the Earth is particularly sensitive to variations in temperature and sea level, leading to a dynamic equilibrium that is continuously adjusting. The movement of molten iron within the outer core generates the magnetic field, a process that is inherently linked to the thermal state of surrounding materials. Increased temperatures at the surface can affect heat exchange processes, potentially altering the flow patterns of these molten materials. Such shifts may result in fluctuations in magnetic intensity. These changes, while gradual, can lead to disturbances in navigation systems reliant on magnetic north. Research indicates that significant climate events can correlate with geomagnetic reversals, periods during which the magnetic poles switch places. While the mechanisms remain under study, the potential influence of climate on these events underscores the interconnected nature of Earth's systems. The effects of anthropogenic activities on the atmosphere may also provoke unforeseen responses in the geodynamo, the very engine behind the magnetic field. Understanding these relationships is essential for comprehending the future trajectory of Earth's magnetic dynamics. The intricate interplay of Earth's magnetic field and animal navigation reveals a remarkable adaptation among species. Many creatures, from birds to sea turtles, utilize magnetic cues to guide their long migrations across vast distances. The magnetic field serves as an invisible map, allowing these animals to traverse landscapes and oceans with precision. This phenomenon is particularly evident in avian species during seasonal migrations. Birds, equipped with specialized receptors, can detect the Earth's magnetic lines, enabling them to orient themselves even when visual landmarks are absent. The ability to perceive subtle shifts in magnetic intensity influences their flight paths, ensuring that they reach their breeding and feeding grounds effectively. Sea turtles also exemplify the reliance on geomagnetic navigation. Hatchlings, emerging from nests along sandy beaches, instinctively move toward the ocean. As they mature, they navigate thousands of kilometers across open water, often returning to the exact beach where they were born, guided by the magnetic field. Shifts in the magnetic field pose potential challenges for these migratory patterns. Alterations in magnetic strength or direction could disrupt established routes, impacting feeding and breeding cycles. Understanding these dynamics is crucial for conservation efforts, as habitats and migratory pathways may be affected by changes in Earth's magnetic environment. The delicate balance of life depends on these invisible forces, underscoring the significance of magnetic navigation in the natural world. Historical magnetic reversals provide critical insights into the behavior of Earth's magnetic field. These events, occurring over hundreds of thousands to millions of years, reveal the dynamic nature of the planet's core. Geological evidence shows that during a reversal, the magnetic field can weaken significantly, allowing increased cosmic radiation to reach the surface. This phenomenon suggests potential implications for life forms that depend on stable magnetic conditions for navigation and protection. Paleomagnetic studies indicate distinct periods characterized by rapid shifts in polarity. The last major reversal, known as the Broomkes-Matuyama transition, occurred approximately 770,000 years ago, Such events are embedded in the stratigraphic record, where layers of sediment and volcanic ash capture the orientation of magnetized minerals. These layers serve as a time capsule, providing a detailed timeline of Earth's magnetic history. Reversals also correlate with shifts in climatic conditions and biodiversity. Fossil records indicate that certain species thrived while others faced extinction during these periods of magnetic instability. The geological implications extend to tectonic activity as well, suggesting that the underlying processes of mantle convection may influence the magnetic field's behavior. Understanding these historical reversals allows scientists to construct models of future magnetic shifts and their potential consequences for Earth's ecosystems and geological stability. The Brunelles's-Matoyama transition, occurring approximately 780,000 years ago, marked a significant change in Earth's magnetic field. This event involved a complete reversal, where magnetic north shifted to what is now magnetic south. Geological records indicate that this transition was not instantaneous, but rather occurred over a period of several thousand years, characterized by fluctuations in magnetic intensity. During this time, the magnetic field weakened, exposing the planet to increased solar and cosmic radiation. These conditions are believed to have had notable implications for life on Earth, potentially affecting migration patterns and evolutionary processes. Fossil evidence suggests that certain species adapted to these changes, while others experienced declines, reshaping ecosystems in ways that continue to be studied. Sediment cores reveal layers with alternating magnetic orientations, providing a clear timeline of this transition. These records help scientists understand the relationship between the geomagnetic field and climatic conditions. The Brunelles's-Matoyama boundary is also associated with significant climate changes, including the onset of glacial periods. The implications of such transitions extend beyond terrestrial environments. The disturbance of the magnetic field can influence satellite operations and power grids, illustrating the interconnectedness of Earth's systems. As the magnetic field continues to drift, ongoing observations will enhance our understanding of these dynamics and their long-term effects on both humanity and the natural world. The historical record of Earth's magnetic field resides within the minerals of ancient rocks. These geological formations capture the orientation of magnetic particles at the moment of their solidification, effectively freezing a snapshot of the planet's magnetic state. This resilience allows scientists to engage in paleomagnetism, a field that deciphers the magnetic history locked within these structures. Each layer of sediment or volcanic rock reveals its own tale, chronicling shifts in the magnetic field over millions of years. Through meticulous sampling and analysis, researchers can reconstruct the movements of tectonic plates and ascertain the field's historical strength and direction. This information serves as a window into past geomagnetic reversals, events when the magnetic poles switch places. The implications extend beyond mere curiosity. Understanding these shifts provides insight into the mechanisms driving the Earth's interior dynamics, including the behavior of the outer core, where molten iron generates the magnetic field. By correlating these findings with fossil records, it becomes evident how organisms adapted to changing magnetic conditions, influencing migration patterns and evolutionary trajectories. The interplay between Earth's magnetic field and geological processes underscores the intricate relationship between the planet's physical properties and its biological inhabitants. Each rock formation, therefore, acts as a silent witness to the past, revealing the complexities of Earth's magnetic narrative. The shifting magnetic field exerts a subtle influence on technology and infrastructure, affecting navigation systems, communication networks, and even power grids. Satellites, which rely heavily on precise positioning, may experience disruptions as the magnetic poles drift. This phenomenon complicates calculations that guide their orbits, leading to potential inaccuracies in data transmission and location services. Ground-based navigational tools, including compasses, encounter increasing inaccuracies as they align with a moving magnetic north. Consequently, adjustments and recalibrations become essential for maintaining reliable direction-finding capabilities. The implications extend to aviation, maritime navigation, and outdoor pursuits, where reliance on accurate compass readings is paramount. In urban environments, power grids face challenges as geomagnetic storms caused by solar activity interact with the magnetic field. These storms can induce electric currents in infrastructure, potentially leading to transformer damage and widespread outages. Utility companies monitor the magnetic field to predict and mitigate such risks, ensuring stability in energy distribution. Telecommunications infrastructure also feels the impact. Radio waves propagate differently under changing magnetic conditions, affecting signal clarity and strength. Engineers must adapt to these variations, optimizing systems to maintain communication integrity. Through these technologies, the changing magnetic field subtly interweaves with modern life, highlighting the delicate balance between nature's forces and human innovation. This delicate balance extends beyond human innovation, linking the shifting magnetic poles to geological activity beneath the Earth's surface. The dynamo effect, resulting from molten iron flowing within the outer core, generates the magnetic field's strength and orientation. Fluctuations in this flow can lead to variations in the magnetic pole's positions, hinting at deeper geological processes at play. These movements correlate with tectonic activity, as shifts in the Earth's crust can reflect changes within its molten layers. Regions experiencing increased seismic events often coincide with notable alterations in magnetic pole locations. This connection suggests a dynamic interaction between surface phenomena and the molten interior, revealing the Earth's ever-evolving nature. Volcanic activity also plays a role in this relationship. Eruptions can release significant quantities of gases and particulates, influencing atmospheric composition and potentially affecting the magnetic field. The release of such materials can alter local magnetic properties, offering insights into the processes driving geological change. Understanding these connections requires a multidisciplinary approach, integrating data from geophysics, geology, and atmospheric science. By examining the movements of the magnetic poles alongside geological events, researchers can develop a more comprehensive picture of the Earth's internal workings. This ongoing inquiry underscores the intricate interplay between Earth's magnetic forces and its geological landscape, a relationship that continues to unfold over time. The interaction between Earth's magnetic field and atmospheric chemistry shapes the very essence of the planet's habitability. It acts as a shield, protecting the atmosphere from solar winds and cosmic radiation. This magnetic barrier plays a critical role in maintaining the delicate balance of gases that sustain life. Charged particles emitted by the sun encounter this field, diverting many away from the Earth's surface and safeguarding the integrity of the atmosphere. The influence of the magnetic field extends to the processes that govern chemical reactions within the atmosphere. This region experiences a continuous flow of ionized particles, which can lead to the formation of secondary pollutants and influence the abundance of greenhouse gases. The dynamics of these interactions are complex, as they are influenced by solar activity and variations in the magnetic field itself. Changes in the magnetic field can induce shifts in atmospheric circulation patterns, which in turn affect weather systems and climate. Fluctuations in solar radiation, moderated by this protective shield, can lead to variations in temperature and pressure. These changes can alter the distribution of ozone and carbon dioxide levels, further impacting atmospheric chemistry. Understanding these connections is essential, as they highlight the profound implications of Earth's magnetic field on not only climate but also on the overall viability of ecosystems across the globe. The magnetic field serves as a vital shield, protecting the planet from the relentless onslaught of cosmic radiation. This radiation originates from various sources, including distant stars and supernovae, posing significant risks to biological life. The interaction between charged particles and the magnetic field results in a deflection of these potentially harmful rays, creating a safe environment where life can thrive. In regions where the magnetic field is weakest, these cosmic rays penetrate more deeply, leading to increased radiation exposure. This exposure can have detrimental effects on living organisms, including enhanced mutation rates and disruptions to cellular processes. The geographic distribution of such radiation exposure is not uniform, revealing the intricate relationship between the magnetic field and environmental conditions. Additionally, the magnetic field plays a crucial role in maintaining the atmosphere's integrity by preventing the erosion of atmospheric particles by solar winds. It sustains the delicate balance of gases essential for life. Without this protective barrier, solar winds could strip away layers of the atmosphere, leading to catastrophic changes in temperature and pressure. The dynamics of the magnetic field, including its gradual drift, underscore its importance in preserving the planet's biosphere. Continuous monitoring of these shifts is necessary to understand their potential long-term impacts on Earth and its inhabitants. This ongoing study remains imperative for assessing future risks to ecological stability. The debate surrounding the magnetic field's potential weakening has garnered significant attention among researchers and scientists. Observations indicate fluctuations in its strength, particularly in this region, where the magnetic field intensity has decreased by approximately 10% over the last 200 years. Such changes prompt inquiries into whether this phenomenon could indicate a more profound, systemic decline. Measurements taken from various locations worldwide reveal a complex pattern. While some areas record diminishing field strength, others exhibit variations that suggest localized anomalies rather than a planet-wide trend. These discrepancies complicate the understanding of overall magnetic health. The hypothesis that the magnetic field may be on the brink of a reversal also surfaces in discussions. A complete reversal, which has occurred multiple times throughout Earth's history, would entail a significant shift in orientation, altering the planet's magnetic poles. Evidence from geological records indicates that reversals can transpire over thousands of years, raising questions about potential impacts on technological systems dependent on magnetic orientation. Simultaneously, the role of the magnetosphere in shielding the planet from solar radiation underscores its importance for life. This protective function becomes critical in light of the ongoing changes, as researchers seek to comprehend the full scope of implications associated with a shifting magnetic field. Understanding these dynamics could provide valuable insight into Earth's future stability. This phenomenon extends beyond geophysical changes, influencing various aspects of life on Earth. The magnetic field, generated by the fluid motion of molten iron in the outer core, acts as a protective shield against solar and cosmic radiation. Its fluctuations can alter exposure levels, which in turn may affect human health. Research indicates that variations in geomagnetic activity could correlate with increased incidences of certain health issues, such as cardiovascular diseases and neurological disorders. Altered magnetic environments have been associated with disruptions in circadian rhythms, influencing sleep patterns and overall well-being. In regions where the magnetic field is particularly weak, populations may experience heightened vulnerability to radiation exposure, leading to an increase in skin cancer and other radiation-related conditions. Studies have also suggested a potential link between geomagnetic storms and mental health challenges, such as anxiety and depression, although the mechanisms remain poorly understood. This intricate relationship between the magnetic field and human health highlights the need for ongoing research. Monitoring changes not only aids in understanding Earth's physical processes, but also offers insight into public health. As these dynamics evolve, so too does the imperative to assess their implications for human society and the environment. Awareness of these effects will be crucial for adaptation and mitigation strategies in the future. The historical reliance on magnetic compasses in navigation marked a significant advancement in maritime exploration. Initially, these instruments were rudimentary, consisting of a magnetized needle floating on a pivot. Their introduction allowed seafarers to determine direction with greater accuracy, offering a newfound confidence in traversing uncharted waters. This transition from celestial navigation to magnetic orientation represented a pivotal moment in human history. Navigators began utilizing compasses extensively during the 13th century, enabling them to chart courses even in overcast conditions. The dependence on this magnetic guidance facilitated trade routes that connected distant lands, fostering economic exchanges across continents. Over time, the design and construction of compasses evolved, incorporating glass casings and more accurate magnetic materials. The compass, however, was not infallible. The magnetic declination, which varies by location, often introduced challenges. Mariners had to adjust their readings based on local magnetic anomalies, a task that required both skill and experience. Despite these hurdles, the compass remained a cornerstone of navigation for centuries. The advent of modern technologies has transformed navigational practices, yet the principles established by early magnetic compasses endure. Understanding the magnetic field's fluctuations and its historical impact on navigation provides insight into contemporary challenges posed by the drifting pole. This knowledge underscores the interconnectedness of past and present in the realm of exploration. The modern applications of magnetometers in earth science illustrate their vital role in understanding magnetic field dynamics. These instruments, capable of detecting minute variations in magnetic fields, are deployed in various settings, providing data essential for studying geomagnetic phenomena. In this region, researchers utilize magnetometers to monitor changes in the Earth's magnetic field, revealing insights into pole shifts and fluctuations. Precision in measurements allows for the tracking of magnetic anomalies, which can signify geological activity beneath the Earth's surface. Such anomalies often indicate the presence of mineral deposits or tectonic movements, guiding exploration efforts in mining and resource management. The data collected also plays a crucial role in navigation systems, enhancing the accuracy and reliability of global positioning technologies. In addition to geological applications, magnetometers contribute to understanding space weather. By monitoring solar winds and their interaction with the Earth's magnetic field, scientists can assess the potential impact on satellite systems and communication networks. This monitoring aids in predicting geomagnetic storms, which can disrupt electronic systems and power grids. Recent advancements have led to the development of portable magnetometers, expanding their use in field studies and environmental assessments. Their versatility enables a deeper exploration of the Earth's magnetic properties, fostering a more comprehensive understanding of both natural processes and anthropogenic influences. Mapping techniques reveal intricate details of the Earth's magnetic field, providing insight into its dynamic nature. Utilizing satellite technology, Researchers capture high-resolution measurements across vast geographical expanses. The intricate dance of charged particles in the magnetosphere influences these readings, allowing for the assessment of variations in magnetic intensity and direction. Ground-based observatories supplement satellite data, offering localized perspectives on geomagnetic activity. These facilities employ magnetometers, sensitive instruments that detect even the slightest fluctuations in magnetic strength. Through a network of such observatories, a cohesive picture of magnetic anomalies emerges, highlighting both temporal shifts and spatial irregularities. Modeling efforts synthesize data from multiple sources, leading to refined representations of the magnetic field. Computational methods incorporate historical data alongside current measurements, enabling the prediction of future movements. This modeling reveals patterns of drift, often illustrating the gradual migration of magnetic poles. The significance of these techniques extends beyond mere observation. They contribute to navigation systems, inform geological studies, and enhance understanding of solar interactions. As the magnetic field continues its subtle yet persistent shifts, these mapping methodologies stand as vital tools, illuminating the complexities of the Earth's protective shield. The interplay of natural forces and human influence unfolds in this ongoing exploration, revealing a world shaped by invisible dynamics. Certain phenomena exhibit intriguing relationships, offering insights into the Earth's complex systems. Changes in the magnetic field, particularly the movement of the poles, have shown a correlation with seismic activity. This region, where tectonic plates converge and diverge, becomes a focal point for studies connecting these two natural occurrences. Variations in the magnetic field may influence subsurface processes, potentially serving as precursors to earthquakes. Measurements indicate that fluctuations in magnetic intensity often coincide with increased seismic events. The movement of molten rock beneath the surface generate electromagnetic signals, which can precede tectonic shifts. These signals serve as essential indicators, providing data that researchers analyze to understand patterns. Geological surveys reveal that certain areas experience heightened earthquake frequency during distinct phases of magnetic field changes. The interplay between these forces suggests a complex dance of energy, where shifts in magnetic lines may alter stress distributions across fault lines. The implications of these findings extend beyond mere observation. They pose questions regarding predictive capabilities in seismology, offering a pathway to potentially mitigate risks associated with earthquakes. Ongoing research seeks to refine this understanding further, aiming to illuminate how the Earth's magnetic field and seismic activity intertwine within the planet's dynamic framework. Volcanism plays a crucial role in shaping the dynamics of the magnetic field. As magma rises from the mantle, it carries with it minerals and metals that possess inherent magnetic properties. Upon reaching the surface, these materials solidify, locking in the magnetic orientation present at that moment. This phenomenon contributes to the creation of magnetic anomalies, which can shift over geological time due to changes in volcanic activity. In regions where active volcanism occurs, the interaction of molten rock with the surrounding environment affects not only local magnetic fields, but also the broader geodynamo process. The movement of conductive materials within the Earth's outer core is influenced by heat generated from these volcanic processes. This interplay can lead to variations in magnetic intensity, altering the orientation of the magnetic poles over time. The cumulative effects of volcanic eruptions, including ash dispersal and gas emissions, further influence atmospheric conditions. Particles released during these events can interact with solar radiation, contributing to fluctuations in ionospheric currents. Such interactions can have downstream effects on the Earth's magnetic field. demonstrating the intricate connections between volcanic activity and geomagnetic changes. These relationships underscore the complexity of the Earth's systems, where volcanism not only shapes landscapes, but also intricately links to the behavior of the magnetic field, guiding ongoing scientific inquiry into these phenomena. Understanding the magnetosphere reveals a protective shield surrounding the Earth formed by the planet's magnetic field. This region extends far into space, where it encounters charged particles from the solar wind. The magnetosphere acts as a barrier, deflecting most of these particles, ensuring that they do not directly impact the atmosphere and surface of the planet. Boundaries within the magnetosphere, such as the bow shock and magnetopause, mark the limits of this protective area. The bow shock forms where the solar wind slows down as it approaches the magnetosphere, creating a region of turbulence. Just beyond this boundary, the magnetopause serves as the outer layer of the magnetosphere, delineating the transition from solar wind influence to the magnetic field's dominance. Within these limits, the dynamics are influenced by various factors, including solar activity. Coronal mass ejections can compress the magnetosphere, creating fluctuations that lead to auroras at the polar regions. These displays of light serve as a visible reminder of the interactions occurring high above the surface. Understanding these boundaries is critical for comprehending how the magnetosphere interacts with external forces. Observations of this region contribute to a broader understanding of space weather, which can have implications for satellite operations and communications on Earth, emphasizing the magnetosphere's role in maintaining planetary stability. The interaction between Earth's magnetic field and solar wind shapes much of the planet's space environment. Solar wind, a continuous stream of charged particles released from the Sun, encounters the magnetosphere, forming a protective barrier around the Earth. This barrier deflects most of the incoming particles, allowing only a fraction to penetrate it, creating conditions that influence both atmospheric phenomena and technological systems. In this complex exchange, the magnetic field lines stretch and distort, responding to the pressure exerted by solar wind. The resulting shapes, known as the magnetotail, can extend far into space, sometimes reaching beyond the orbit of the Moon. When solar activity increases, such as during coronal mass ejections, the intensity of these interactions can lead to geomagnetic storms. These storms can induce currents in Earth's surface, affecting power grids and navigation systems. Regions near the poles experience more pronounced effects, allowing charged particles to enter the atmosphere and create auroras. This phenomenon occurs when solar wind particles collide with atmospheric gases, resulting in spectacular displays of light. The extent of these occurrences correlates with solar activity cycles, revealing the dynamic connection between the Sun and Earth. Understanding these interactions is essential for predicting space weather events and safeguarding technological infrastructure, illustrating the intricate balance maintained by the planet's magnetic shield. The interplay between solar particles and Earth's magnetic field gives rise to breathtaking auroras, phenomena that illuminate polar skies. Charged particles, ejected from the Sun's corona, enter the upper atmosphere, colliding with atmospheric gases. This interaction generates light, producing vivid colors that dance against the night. The formation of these displays occurs predominantly near the magnetic poles, where the field lines converge. This region acts as a gateway, funneling particles into the atmosphere. At altitudes between 100 kilometers and 300 kilometers, oxygen and nitrogen atoms become excited during these collisions, emitting light in various hues. Oxygen can produce green and red shades, while nitrogen contributes blues and purples. Seasonal variations and solar activity influence the frequency and intensity of auroras. During solar storms, enhanced solar wind can lead to more intense displays, often visible at latitudes far beyond the polar regions. This transformation of energy emphasizes not only the beauty of these lights, but also the complex mechanisms at play. The patterns observed are not random. They often align with the magnetic field's structure. Understanding these patterns provides insights into the behavior of charged particles and the broader dynamics of Earth's atmosphere. These radiant arcs serve as a reminder of the planet's ongoing relationship with the cosmos, a relationship that continues to unravel mysteries of our existence. Fluctuations in the magnetic field significantly influence space weather, which in turn affects satellites orbiting the Earth. Variations in this invisible shield can create disturbances in the charged particles of the solar wind, leading to heightened levels of radiation and electromagnetic activity. Satellites, operating in a delicate balance, are particularly vulnerable to these shifts. When the magnetic field weakens or shifts, the protective barrier that normally safeguards these machines becomes less effective. Increased radiation exposure can disrupt their electronic systems, leading to potential malfunctions or complete failures. This region, where terrestrial influences meet cosmic forces, is marked by a delicate interplay, necessitating constant monitoring. Data collection from these satellites allows scientists to understand the dynamics of space weather and its impacts on operational technology. Adjustments in satellite orbits and shielding measures are often required to mitigate risks associated with solar storms and magnetic anomalies. The consequences of these disturbances extend beyond the immediate technological challenges, influencing communication systems, navigations, alders, and even power grids on the ground. The ongoing study of these phenomena illustrates the intricate connections between Earth's magnetic field and the broader solar environment. Insights gained from such investigations contribute to developing strategies that enhance the resilience of satellites against the unpredictable nature of space weather. The potential risks of a reversal of the magnetic poles extend beyond mere curiosity. This phenomenon, while infrequent, raises concerns regarding its implications for Earth and its inhabitants. During a reversal, the magnetic field weakens significantly, creating vulnerabilities in the planet's protective shield. Cosmic radiations, which is usually deflected, could penetrate deeper into the atmosphere. Such an increase in exposure may lead to heightened risks of skin cancer and other health issues among living organisms. The consequences are not confined to biological effects. Modern technology, heavily reliant on satellite systems, could also be disrupted. Navigational systems, such as GPS, may experience inaccuracies, leading to potential challenges in transportation and communication, particularly in critical operations like aviation and maritime activities. Animal species that depend on the magnetic field for navigation could exhibit disorientation, affecting migration patterns and food chains. This disruption may lead to long-term ecological consequences, altering the balance of ecosystems. Geological activity could also be influenced, with the magnetic field acting as a shield against solar winds. A weakened field might provoke increased geological events. The stability of power grids may be compromised, resulting in outages and infrastructure strain. Understanding these potential risks emphasizes the importance of ongoing research into Earth's magnetic field dynamics and the need for preparedness in the face of such changes. Several theories attempt to elucidate the causes behind the movement of Earth's magnetic field. The geodynamo process stands central among them, driven by the motion of molten iron alloys in the outer core. These convective currents create electric currents, which in turn generate magnetic fields. Variations in temperature and composition within this region introduce complexities, leading to the observed fluctuations in the magnetic field's intensity and position. Another theory relates to the influence of tectonic activity. As the plates shift and collide, they can alter the flow of materials within the mantle, which may indirectly affect the dynamo activity. This interaction between surface geology and magnetic field dynamics suggests a deeper connection between terrestrial processes and geomagnetic phenomena. Some researchers also consider external factors, such as solar activity. Changes in solar wind and cosmic rays can induce alterations in the magnetosphere, potentially influencing the overall magnetic field. These interactions highlight the delicate balance between external cosmic forces and internal geophysical processes. Recent advancements in satellite technology have allowed for more precise measurements, contributing to a deeper understanding of these movements. Observations reveal that the magnetic poles are not static, but instead engage in a slow, complex dance, with implications that extend beyond Earth itself, affecting navigation systems and animal migration patterns on a global scale. Convection currents in the outer core play a pivotal role in generating and sustaining Earth's magnetic field. These currents arise from the intense heat produced by the decay of radioactive isotopes and the residual heat from the planet's formation. As molten iron and nickel circulate, they create a dynamic system, with hot material rising toward the upper layers and cooler material sinking toward the depths. This movement induces electric currents, which in turn produce magnetic fields. The complexity of these convection currents is influenced by various factors, including temperature gradients and the composition of the molten metal. Variations in flow velocity and direction contribute to fluctuations in the magnetic field, leading to the observed motion of the magnetic poles. This process is not uniform. It is characterized by irregularities and turbulence, which can accelerate shifts in pole locations. Pixay resonchiftum kunsoglingsonins. In this region, the interaction between the flowing conductive materials and the existing magnetic field results in a self-sustaining dynamo effect. The continuous reconfiguration of these currents can lead to significant changes over time, including pole reversals. Such events, while infrequent, have occurred numerous times throughout geological history, each leaving a distinct imprint on the planet's magnetic signature. Understanding these processes provides critical insight into the inner workings of Earth and the implications for surface phenomena. Mantle dynamics play a pivotal role in shaping the magnetic field. This region, composed of semi-solid rock, undergoes convection, resulting in the gradual movement of material. Such movements create complex interactions that influence electrical conductivity and, consequently, the geomagnetic field. The flow of molten rock generates currents that contribute to the geodynamo mechanism, responsible for producing and maintaining the magnetic field. Variations in temperature and pressure within the mantle lead to the formation of plumes and other geological structures. These features can alter the flow patterns of the mantle, creating localized anomalies in the magnetic field. In some instances, these anomalies manifest as deviations in compass readings, impacting navigation and other surface activities. The connection between mantle dynamics and the magnetic field extends to the concept of magnetic reversals. During specific intervals in geological history, the magnetic poles have flipped, a phenomenon linked to changes in mantle convection patterns. Such reversals illustrate the dynamic nature of Earth's interior and its influence on the magnetic field. The study of these relationships is essential for understanding the long-term stability of the magnetic field. It sheds light on the potential consequences of ongoing shifts within the mantle, offering insights into the future behavior of Earth's magnetic environment and its effects on life and technology. The movement of tectonic plates plays a critical role in shaping the dynamics of Earth's magnetic field. As these plates drift and interact, They contribute to variations in the underlying magma flow within the mantle. This shifting of the mantle can influence the geodynamo process, which generates the planet's magnetic field. Changes in the rate and direction of these plate movements can lead to localized anomalies in magnetic intensity, further complicating the magnetic landscape. Observations reveal that regions near tectonic boundaries often display fluctuations in magnetic strength, suggesting a direct link between lithospheric activities and geomagnetic properties. These interactions can result in the formation of new magnetic features, such as magnetic reversals, where the north and south poles switch places. Such reversals occur irregularly, with geological records indicating that they happen approximately every 250,000 years, although this interval can vary significantly. The implications of these processes extend beyond geology. The shifting magnetic field can affect satellite communications and navigation systems, which rely on stable magnetic references. Changes in magnetic intensity can also influence the behavior of charged particles in the atmosphere, potentially impacting electrical grids and technology. Understanding these interconnections is essential for predicting future shifts and mitigating their effects on modern life and infrastructure. The relationship between the magnetic field and Earth's climate history reveals intricate patterns of change. Fluctuations in geomagnetic intensity have been observed to coincide with significant climatic events, periods of magnetic field reversals, when the magnetic north and south poles switch, often align with alterations in atmospheric composition and temperature. These reversals, occurring every several 100,000 years, coincide with paleoclimatic records, indicating shifts in ocean currents and global temperature. During these transitions, the magnetic field's protective qualities diminish, allowing increased solar radiation to penetrate the atmosphere. This exposure can influence climate systems, contributing to cooling or warming phases that alter ecosystems globally. In some instances, the magnetic field has weakened significantly, leading to episodes of heightened solar activity impacting Earth's climate. Such events provide a glimpse into how the magnetic field's behavior can serve as a barometer for broader environmental changes. The complexity of this relationship illustrates that Earth's climate is not solely dictated by atmospheric factors, but is also influenced by geophysical processes beneath the surface. These dynamics are crucial in understanding historical climate variations, offering insights into how current fluctuations in the magnetic field might foreshadow future climatic scenarios. The interplay of magnetic forces and climate history continues to be a profound area of study, informing predictions and adaptive strategies for the future. The South Atlantic anomaly represents a significant deviation in Earth's magnetic field. This region, characterized by a weakened magnetic field strength, extends over parts of South America and the South Atlantic Ocean. The anomaly arises from the complex interactions between the liquid ion movements within the outer core and the overlying mantle dynamics discovered in the late 20th century. It presents a unique challenge for satellite and space mission operations, exposing these systems to increased radiation levels. This heightened radiation environment can disrupt electronic components, leading to data loss or malfunction. Monitoring this anomaly has become crucial for ensuring the reliability of satellite technology and understanding its implications for space weather. The geographical extent of the anomaly highlights the dynamic nature of the magnetic field, illustrating how it can fluctuate over time. Research indicates that this region is a remnant of historical magnetic field configurations, serving as a window into the planet's geological past. The variability of the anomaly also raises questions about the future stability of the magnetic field, prompting scientists to investigate potential links to broader geophysical phenomena. Continued study of the South Atlantic anomaly sheds light on the intricate relationship between Earth's magnetic field and its geological processes, contributing valuable insights to the understanding of this ever-evolving planet. Geomagnetic secular variation plays a significant role in the dynamics of Earth's magnetic field. Reflecting gradual changes over time, these variations can be attributed to the complex movements within the outer core, where molten iron generates the magnetic field through dynamo processes. The fluctuations in these movements contribute to the shifting nature of the magnetic field, providing a glimpse into the inner workings of Earth's core. Observations indicate that the intensity of the magnetic field varies across different regions, with certain areas experiencing significant decreases. This weakening not only affects navigation systems but also influences the radiation environment that reaches the surface. Understanding these secular variations helps researchers predict future shifts and their potential impacts on technology and life on Earth. The interplay between geomagnetic anomalies and secular variation is particularly important. Anomalies, such as those found in the South Atlantic, may signal underlying changes in the geodynamo's behavior. Such insights are crucial for comprehending the magnetic field's response to external forces, including solar activity and tectonic movements. Studying these variations also offers a window into past geomagnetic events, enabling scientists to reconstruct historical changes. This knowledge provides context for current shifts and enhances the overall understanding of Earth's magnetic environment, emphasizing its significance in the broader scope of planetary science. Comparisons with other planetary magnetic fields reveal distinct characteristics and behaviors. Mars, for instance, exhibits localized magnetic anomalies rather than a global field, resulting from its geological history and lack of a substantial dynamo effect. This absence of a protective magnetic shield exposes the Martian surface to solar winds, leading to atmospheric erosion over time. Jupiter, in stark contrast, possesses an immense magnetic field generated by its rapid rotation and the movement of metallic hydrogen within its interior. This magnetic environment is approximately 20 times stronger than Earth's and extends far beyond its atmosphere, trapping charged particles in a vast magnetosphere. Such differences illustrate the diverse evolutionary paths taken by planetary bodies. The magnetic fields of gas giants like Saturn follow similar principles, but show variations in complexity and intensity. Saturn's field is also generated by metallic hydrogen, but its unique rotation and internal dynamics create a unique interaction with its moons, influencing their geological features and potential habitability. Venus, lacking a significant magnetic field, provides another point of interest. The interaction between solar wind and its thick atmosphere leads to complex processes, contributing to a highly dynamic environment. These comparisons not only deepen the understanding of Earth's magnetic field, but also highlight the intricate interplay between magnetic forces and planetary evolution across the solar system. Magnetic field anomalies present in various regions provide vital clues about geological processes beneath the surface. These irregularities indicate variations in the Earth's crust and the presence of mineral deposits often linked to tectonic activity. Certain areas exhibit significant magnetic fluctuations, suggesting the influence of ancient volcanic events or tectonic shifts. This region, characterized by its unique geological features, serves as a natural laboratory for understanding the history of plate movements. Geological formations associated with these anomalies reveal the remnants of past magnetic orientations, which can be crucial for reconstructing the planet's geological timeline. The record preserved in rocks indicates periods of geomagnetic reversals, where the magnetic poles switch positions. Anomalies allow scientists to examine how these events correlate with geological phenomena such as mass extinctions or climate shifts. Additionally, localized magnetic disturbances may signal the presence of mineral wealth, including deposits of iron and nickel. Exploring these anomalies not only aids in resource identification, but also enhances comprehension of the Earth's magnetic history. Each anomaly serves as a chapter in the ongoing story of planetary formation and transformation, revealing the complexities of a dynamic Earth. By studying these regions, researchers can piece together a broader view of how magnetic forces shape geological landscapes over time. The interactions between magnetic fields and biological systems reveal complex relationships that influence life on Earth. Certain species, such as migratory birds, exhibit an innate ability to navigate using the Earth's magnetic field. Specialized cells containing magnetite, a magnetic mineral, are believed to play a crucial role in this orientation. These cells essentially allow organisms to perceive magnetic fluctuations, providing a biological compass that guides them across vast distances. In addition to navigation, magnetic fields impact the behavior and development of various organisms. Some studies suggest that changes in geomagnetic intensity can affect reproductive cycles in certain fish and amphibians. The sensitivity of these life forms to magnetic variations highlights the fundamental role of magnetic fields in the ecological balance of their environments. This influence extends to phytoplankton, the microscopic organisms that underpin the marine food web. Variations in magnetic activity can affect their growth and distribution. Research continues to uncover how magnetic fields may also influence human health, while the effects remain a subject of ongoing inquiry. Some studies have indicated that exposure to magnetic fields could affect sleep patterns and circadian rhythms. Understanding these interactions is essential for comprehending the broader implications of Earth's magnetic dynamics. New geophysical techniques have emerged, enhancing the ability to monitor and study the magnetic field's fluctuations. Satellite missions, such as the Swarm constellation, provide detailed three-dimensional maps of magnetic variations across the globe. These satellites utilize precise magnetic sensors to detect changes in the Earth's magnetic field with unprecedented accuracy. Ground-based observatories complement these satellite observations, offering localized data that helps scientists understand regional anomalies. Advanced magnetometers, deployed in strategic locations, measure variations in magnetic intensity, contributing critical insights to the overall picture of geomagnetic behavior. The integration of these diverse data sources allows for the creation of sophisticated models that simulate the magnetic field's dynamics. These models are essential for predicting future shifts and understanding their potential impact on technology and navigation systems. In addition to satellite and ground-based techniques, numerical simulations are utilized to study the complex interactions within the Earth's core that generate the magnetic field. By simulating various scenarios, researchers can explore how changes in the core's flow patterns affect the magnetic field on the surface. This multifaceted approach not only advances scientific knowledge, but also enhances the ability to mitigate risks associated with magnetic field variations, such as disruption of communication systems and navigation technologies. The ongoing refinement of these techniques continues to unveil the intricate behaviors of Earth's magnetic dynamics. Numerical models serve as essential tools in predicting changes within the magnetic field. These computational frameworks utilize complex algorithms to simulate the geodynamo processes occurring within Earth's outer core. By integrating vast datasets, they can replicate the fluid motion of molten iron, and the resultant magnetic field generation. This accuracy allows researchers to forecast the trajectory of pole shifts and fluctuations in magnetic intensity. Recent advancements in computational power have enhanced the resolution of these models, enabling them to capture finer details of magnetic field behavior. These intricate simulations reveal patterns that would be difficult to discern through observational data alone. The outputs of these models provide insights into the potential impacts on navigation systems, satellite communications, and even climate patterns. In addition to predicting pole movement, numerical models also investigate the historical context of magnetic field changes. By simulating past conditions, scientists can better understand how current shifts align with historical trends. This historical perspective is crucial for discerning patterns and anomalies that may indicate broader geological processes at play. These predictive capabilities are vital for preparing for potential disruptions. While the exact timeline of future shifts remains uncertain, the continuous refinement of numerical models offers a clearer understanding of the magnetic field's dynamic nature. This ongoing research contributes significantly to our comprehension of Earth's inner workings and their implications for life on its surface. The future of Earth's magnetic field remains a subject of considerable interest among scientists. Predictions about its behavior encompass a range of scenarios, fostering a deeper understanding of potential changes ahead. Current models suggest that the magnetic field may continue to weaken, a phenomenon observed over the past 2 centuries. This decline raises questions about its ability to shield the planet from solar and cosmic radiation. Gradual shifts in the magnetic poles could lead to increased exposure to these energetic particles, impacting technological systems on Earth. Satellites, communications, and navigation systems may experience disruptions as the field fluctuates. Some researchers posit that a complete magnetic reversal could occur within the next several thousand years, a process marked by the poles swapping positions. Historical evidence indicates that such reversals have happened multiple times, each lasting thousands of years. Consequences of these events might not be immediate. However, the gradual changes in the magnetic environment could influence climatic patterns and geological activity over extended periods. Monitoring efforts in this region of study are paramount, as they allow scientists to refine models and improve predictions. The ongoing exploration of Earth's magnetic dynamics continues to shed light on the intricate balance that sustains life, bridging the past, present, and future in a quest for knowledge about our planet's magnetic identity. Variations in the magnetic field exert a significant influence on technology, especially in a world increasingly reliant on electronic systems. This region, where the magnetic field fluctuates, can disrupt satellite communications, navigation systems, and power grids. They experience disturbances that may lead to inaccuracies in positioning, rendering global positioning systems less reliable. The consequences can ripple through various sectors, from aviation to maritime navigation, presenting challenges that require careful management and adaptation. Power grids, especially those at higher latitudes, are vulnerable to geomagnetic storms caused by solar activity. These storms induce currents that can overload transformers, leading to potential blackouts or infrastructure damage. Engineers and scientists closely monitor these fluctuations, employing advanced models to predict and mitigate their effects, ensuring that electricity remains a stable resource. In the realm of telecommunications, variations can lead to signal degradation and disruptions. Radio waves, which rely on the ionosphere, can be affected by the changing magnetic field, causing interruptions in service. Research into these phenomena plays a critical role in developing resilient technologies that can withstand such challenges. Wells say understanding the interconnectedness of magnetic field variations and technology enhances our preparedness for potential impacts. This ongoing study serves as a reminder of the delicate balance between natural forces and human innovation, underscoring the importance of resilience in the face of change. The integration of satellite data has revolutionized the monitoring of magnetic field changes. These advanced instruments, orbiting high above the planet, collect comprehensive information about variations in Earth's magnetic field with remarkable precision. The data captured offers a continuous stream of insights, revealing fluctuations that occur on both large and small scales. Equipped with sensitive magnetometers, satellites can detect shifts in magnetic intensity and direction, providing a global perspective that was previously unattainable. This capability allows researchers to analyze the influence of geological structures and atmospheric conditions on magnetic behavior. Understanding these influences is crucial for predicting the future trajectory of the magnetic poles. Data from missions such as the Swarm satellite constellation have enhanced the ability to map magnetic anomalies in unprecedented detail. These anomalies, often linked to subterranean formations, reveal the intricate relationship between the Earth's crust and its magnetic field. Such information is critical for assessing the potential impacts on navigation systems and electronic infrastructure, both of which rely heavily on stable magnetic environments. Additionally, long-term satellite observations contribute to the understanding of secular variation, a gradual change in the magnetic field over time. By collating years of data, scientists are piecing together a clearer picture of the mechanisms driving these changes, ensuring informed responses to their implications. Long-term monitoring programs play a critical role in understanding the dynamics of Earth's magnetic field. These initiatives provide a continuous stream of data, capturing subtle shifts that might otherwise go unnoticed. With instruments strategically placed across various regions, they facilitate real-time observations of magnetic fluctuations. This data is essential for identifying trends that evolve over decades or centuries, offering insights into the complex interactions within the Earth's core. In addition to tracking the magnetic poles, these programs enhance knowledge of geomagnetic storms, which can disrupt communication systems and satellite operations. By maintaining a vigilant watch over these phenomena, scientists can develop predictive models that inform infrastructure resilience strategies. The impact of solar winds on the magnetic field is also better understood through sustained monitoring, as it reveals how external cosmic events affect terrestrial systems. As the magnetic field continues to shift, historical records provide context. These long-term datasets enable researchers to establish baselines, allowing for comparisons with contemporary measurements. Such comparisons reveal anomalies and assist in forecasting potential future shifts. The collaboration between various global monitoring stations creates a network of knowledge that is invaluable for addressing the challenges posed by magnetic field changes. The influence of magnetic phenomena extends far beyond scientific inquiry, weaving itself into the very fabric of human culture throughout history. Ancient civilizations often revered magnetic forces, attributing spiritual significance to the compasses and lodestones that guided navigators across vast oceans. These natural magnets were perceived as mystical objects, believed to possess inherent powers that aligned with celestial bodies, aiding in both exploration and navigation. In various cultures, magnetic anomalies inspired mythologies and legends, with magnetic mountains or islands depicted as sacred places. The interplay between these phenomena and human perception fostered a sense of awe and reverence. Ancient astronomers, observing the night sky, often correlated magnetic shifts with celestial events, further linking terrestrial and cosmic phenomena in their understanding of the universe. The advent of the scientific revolution brought a more empirical approach, yet cultural reflections persisted. Literature and art continued to explore magnetism's duality, encapsulating both its tangible effects and intangible mysteries. The romantic allure of the magnetic compass became a symbol of adventure, freedom, and the quest for knowledge. This historical context reveals the deep connection between humanity and magnetic phenomena, illustrating how these forces have shaped not only practical navigation, but also cultural identity across centuries. The legacy of this relationship endures, influencing modern perspectives on the dynamic Earth. Earth travel relies heavily on precise navigation systems, which are intricately tied to Earth's magnetic field. As the poles shift, these systems must adapt to ensure safety and efficiency in aviation. This region, where the magnetic field is becoming increasingly unstable, presents challenges for pilots who depend on magnetic compasses for guidance. As the magnetic declination alters, navigational accuracy can be compromised, potentially leading to miscalculations during flight. Onboard instruments continually update their readings, yet the shifting magnetic landscape necessitates frequent recalibration to maintain reliability. These adjustments are essential, especially for long-haul flights that traverse vast expanses where reliance on magnetic bearings becomes paramount. The fading company of traditional navigation systems is gradually being supplemented by advancements in satellite technology, which offers alternatives that are less susceptible to these fluctuations. This transition to more modern navigation techniques reduces the potential risks associated with magnetic variations. Nevertheless, awareness of the magnetic field's movements remains crucial. Aviation authorities monitor these changes closely, implementing updated protocols and training for pilots to ensure continued safety in the skies. The interaction between technology and the natural world illustrates the delicate balance that governs air travel, underscoring the importance of understanding our planet's magnetic dynamics in maintaining airborne security. The contributions of citizen science have become vital in the study of magnetic field fluctuations. Engaged individuals across various regions are now equipped to assist in gathering data, creating a network that expands the reach of traditional scientific methods. These participants utilize simple tools to record magnetic readings, allowing for a broader understanding of local anomalies and their potential implications on larger scales. Observations made by enthusiasts often complement the rigorous measurements taken by professional researchers. This collaboration enriches the dataset available for analysis, facilitating a more comprehensive view of the magnetic shifts occurring globally. The geographic diversity of volunteer contributions reveals patterns that may be overlooked in isolated studies, enhancing the understanding of how these changes affect different ecosystems. This grassroots involvement not only fosters a sense of community, but also empowers individuals to contribute to significant scientific inquiries. Each recorded measurement adds to a growing repository of knowledge, helping scientists identify trends and assess the pace at which the magnetic poles are migrating. The integration of amateur observations with advanced technology creates a more nuanced understanding of the Earth's magnetic environment. In an era where the effects of climate change and human activity are increasingly evident, this combination of expertise and public engagement in magnetic field research highlights the importance of collective efforts in understanding and addressing the challenges posed by an ever-changing planet. The influence of the magnetic field on weather patterns is a complex interplay of forces that has intrigued scientists for decades. This region of the atmosphere, where charged particles interact with the Earth's magnetic forces, plays a significant role in shaping climatic conditions. Variations in the magnetic field can affect solar radiation levels reaching the surface, which in turn influences temperature fluctuations. These alterations may contribute to changes in wind patterns, as the distribution of heat across the planet is modified. Such shifts can lead to alterations in precipitation patterns, affecting ecosystems and human settlements alike. For instance, regions that typically experience consistent rainfall may face unexpected droughts, while others may encounter increased flooding due to enhanced storm activity. The interconnectedness of magnetic and atmospheric phenomena underscores the delicate balance within Earth's systems. Research indicates that disturbances in the magnetic field can correlate with shifts in weather anomalies, revealing a subtle yet profound connection. As data collection advances, the implications of these findings become clearer, presenting opportunities for improved climate modeling. Understanding the magnetic field's influence on weather patterns allows for better forecasting and preparedness, essential in a world grappling with environmental uncertainties. This ongoing exploration emphasizes the intricate web of influences that govern our planet's climate dynamics. Connections between the magnetic field and ocean currents reveal a complex interplay that influences climate patterns globally. Variations in the magnetic field can affect the behavior of charged particles in the ocean, leading to changes in circulation patterns. These currents, in turn, play a significant role in regulating temperatures and distributing heat across different regions. The movement of oceanic water is largely driven by wind patterns, but the underlying magnetic properties also contribute to the dynamics of currents. As the magnetic field shifts, it can modify the routes that warm and cold water take, thereby impacting regional climates. These alterations can lead to significant fluctuations in weather systems, influencing everything from monsoonal cycles to the occurrence of extreme weather events. This relationship is evident when observing shifts in ocean temperatures, which directly correlate with changes in the magnetic field. Scientists employ satellite technology to monitor these shifts, allowing for a greater understanding of how these two systems interact over time. Data gathered from these observations contribute to predictive models that aim to forecast future climate scenarios. Understanding this interconnectedness is essential for comprehending the broader implications of magnetic field movements, particularly regarding their influence on global weather patterns and the long-term stability of marine ecosystems. The delicate balance maintained by these forces is central to the health of our planet. The role of Earth's magnetic field extends far beyond the confines of its atmosphere. This invisible shield interacts with solar winds, which are streams of charged particles emitted by the sun. These interactions shape a protective barrier known as the magnetosphere, which envelops the planet and extends into space. Within this region, charged particles are deflected, diminishing their potential to strip away the atmosphere. This magnetic presence not only safeguards life on Earth, but also plays a crucial role in maintaining stability within the solar system. By influencing the trajectories of cosmic particles, it contributes to a dynamic equilibrium that facilitates the orbits of celestial bodies. These protective properties become especially vital during solar flares, which are sudden eruptions of energy on the sun's surface. The magnetic field's ability to absorb and redirect these bursts prevents severe disruptions that could impact communication systems and satellite operations. The magnetic field's gradual drift is also significant. It reflects shifts in the flow of molten iron within the outer core, a process that determines its strength and configuration. Changes in this field can alter the magnetosphere's structure, influencing how Earth interacts with other planetary bodies and solar phenomena. Such variations remind us of the intricate connections within the solar system and the delicate interplay between celestial forces, shaping not just Earth's environment, but the broader cosmic landscape. Planetary maintain. Magnetic field stability is an essential aspect of Earth's geophysical processes. It provides a protective barrier against solar radiation and cosmic rays, influencing not only the atmosphere, but also the conditions necessary for life. Variations in this stability can have profound implications. An unstable magnetic field may lead to increased exposure to harmful radiation, potentially disrupting technological systems and biological organisms. Regions of instability are often characterized by erratic fluctuations in magnetic intensity. These fluctuations can arise from the dynamic movements within the outer core, where molten iron generates the magnetic field through convection currents. The complex interactions between these movements contribute to the field's shifting nature. As the magnetic poles drift, they may also affect navigation systems and migratory patterns of various species that rely on geomagnetic cues for orientation. Understanding these instabilities illuminates how they may have evolved over geological time. Past records indicate that magnetic reversals, where the north and south poles swap places, have occurred at irregular intervals. Each reversal serves as a reminder of the volatile nature of Earth's interior and the mechanisms driving these transformations. Such insights not only provide a window into the planet's past, but also reinforce the interconnectedness of Earth's systems and their responses to both internal and external forces, shaping the environment we inhabit today. Theoretical models of magnetic reversals offer a structured understanding of how the geomagnetic field can shift in polarity over time. These processes are rooted in the complex dynamics of the Earth's outer core, where molten iron and nickel flow generate the magnetic field through a mechanism known as the geodynamo. Variations in temperature, pressure, and movement of these conductive materials can lead to instabilities, prompting the magnetic poles to reverse. The mechanisms behind these reversals remain an area of active research. Some theories propose that changes in the convection patterns within the outer core may disrupt the existing magnetic field, leading to significant fluctuations before a complete reversal occurs. The duration of these events spans thousands to millions of years, with intervals of stability interspersed with rapid transitions. Schaft polycores to the Nischensporschenarches, paleomagnetic evidence from ocean floor sediments and volcanic rocks provides crucial data on the timing and frequency of these reversals. Patterns in the magnetic signature reveal periods of relative stability followed by abrupt changes, suggesting that the process is influenced by various geological and hydrodynamic factors. Understanding these mechanisms not only sheds light on the Earth's magnetic history, but also has implications for technological systems dependent on the stability of this field. Each model continues to refine the comprehension of how these shifts impact the planet and its inhabitants. Understanding the implications of magnetic field changes extends beyond mere scientific curiosity. The shifting poles influence navigation systems, critical for both civilian and military operations. Global positioning systems rely on stable magnetic references, which are now subject to alteration. As they drift, adjustments must be made to maintain accuracy, impacting air travel, maritime navigation, and even financial transactions dependent on precise location data. National security concerns arise as these changes can affect the effectiveness of communication systems. Satellites, essential for reconnaissance and intelligence gathering, may experience disruptions. Countries with advanced technological infrastructures must adapt to these variations, ensuring that their systems remain resilient against potential vulnerabilities. Moreover, The interplay between magnetic shifts and climate patterns could reshape geopolitical landscapes. Changes in regional weather systems, potentially tied to alterations in the magnetic field, may influence agricultural productivity. Regions previously suitable for farming could become less viable, prompting shifts in population and resource allocation. These dynamics may also heighten competition over dwindling resources, particularly in areas affected by changing climatic conditions. The Arctic, for instance, could see an influx of interest as ice melts and new pathways emerge. Nations might vie for dominance in these regions, driven by the prospect of untapped natural resources. In this evolving context, the interconnectedness of science, technology, and geopolitics becomes increasingly evident. An informed populace plays a crucial role in navigating the complexities of magnetic field science. Educational institutions serve as the foundational pillars for understanding the dynamic nature of Earth's magnetic field. Through comprehensive curricula that cover geology, physics, and environmental science, students gain insights into the forces that govern planetary behavior. Laboratories and field studies deepen this understanding, allowing learners to observe phenomena firsthand. These experiences foster critical thinking and problem-solving, essential tools for future scientists. Research initiatives often emerge from academic settings, contributing to the broader body of knowledge regarding pole shifts and their implications. Partnerships between universities and research organizations facilitate the exchange of expertise, enabling advanced studies of magnetic variations. Public outreach programs extend this knowledge beyond academia, encouraging community engagement with scientific concepts. Informative lectures, workshops, and interactive exhibits provide accessible avenues for exploration. The role of education extends into policymaking, where scientifically literate individuals can influence decisions on resource management and environmental protection. Understanding magnetic fields is not merely an academic pursuit. It has tangible effects on navigation, communication, and even climate understanding. In a world increasingly affected by rapid changes, a well-rounded education ensures that society is equipped to address the challenges posed by shifting magnetic poles, fostering resilience in the face of uncertainty. The future of magnetic field research presents both challenges and opportunities that will shape our understanding of Earth's dynamics. This field of study is entering a new era, driven by advancements in technology and an increasing need for precise data. Sophisticated satellite missions are being deployed to monitor changes in the magnetic field with unprecedented accuracy. These tools are capable of capturing minute fluctuations that were previously undetectable, allowing researchers to develop more comprehensive models of geomagnetic behavior. Data collection from various sources, including ground-based observatories and airborne surveys, enhances the scope of research. The integration of artificial intelligence facilitates the analysis of vast datasets, revealing patterns and trends that inform our understanding of magnetic reversals and secular variation. This detailed approach aids in forecasting potential impacts on navigation systems, wildlife migration, and even climate patterns. Challenges arise from the inherent complexity of geomagnetic phenomena. The chaotic nature of Earth's core dynamics can complicate predictive modeling, often leading to uncertainties. Furthermore, funding and resource allocation for long-term research initiatives remain critical factors in sustaining progress. Engaging interdisciplinary collaboration between geophysicists, climate scientists, and data analysts will be essential in navigating these obstacles. Together, These efforts will deepen our comprehension of the magnetic field's role in Earth's evolving systems and its importance for future generations. International collaboration in geomagnetic studies serves as a cornerstone for understanding the complexities of Earth's magnetic field. Multiple nations contribute unique datasets, each bringing distinct methodologies and perspectives to the field. This convergence of knowledge fosters a comprehensive approach to deciphering the intricate behaviors of geomagnetic fluctuations. Collaborative efforts often lead to the establishment of global monitoring networks, allowing for real-time data collection across diverse geographical locations. Shared research initiatives facilitate the pooling of resources, enabling scientists to conduct large-scale magnetic surveys that would be impractical for individual countries. The insights gained from these extensive studies illuminate the connections between geomagnetic activity and phenomena such as climate change and natural disasters. When researchers from different regions share their findings, they enhance the reliability of predictive models, crucial for anticipating shifts in magnetic polarity and their potential impacts on technology and ecology. This cooperative framework extends beyond data sharing. It fosters educational exchanges that cultivate a new generation of scientists. By learning from one another, researchers can develop innovative techniques and strategies that propel the field forward. Through collaborative partnerships, the scientific community can address pressing challenges related to geomagnetism, ensuring that knowledge is not confined to borders, but rather disseminated for the benefit of all. The collective effort signifies a unified approach to unraveling the mysteries of the magnetic forces that shape our planet. Urbanization has introduced significant alterations to local magnetic fields, driven primarily by the proliferation of ferromagnetic materials and the extensive electrical infrastructure that cities necessitate. This region, now densely populated, features an array of structures composed of steel and concrete, which inherently possess magnetic properties that can distort the natural geomagnetic landscape. These modifications extend beyond mere construction materials. The widespread use of electrical devices generate electromagnetic fields that can disrupt the ambient magnetic environment. Urban centers often display localized anomalies where the magnetic field strength deviates from expected values due to these anthropogenic influences. This phenomenon not only poses challenges for navigation systems reliant on magnetic orientation, but also affects geological and geophysical research conducted within urban settings. The interaction between human activity and the magnetic environment raises questions about the long-term implications for both local ecosystems and geomagnetic studies. Monitoring these shifts provides valuable insights into how urban growth shapes the magnetic landscape. Understanding these changes is essential for future planning and technological applications, as well as for assessing potential impacts on wildlife that rely on magnetic cues for migration and navigation. As cities continue to expand, the complexities of urbanization will likely evolve, further influencing local magnetic fields and prompting ongoing research into their broader implications. The dynamics of this relationship remain a focal point of scientific inquiry. Geology provides essential insights into the shifting nature of the magnetic field. The various layers of Earth, from the crust to the mantle, harbor minerals that capture the planet's magnetic orientation at distinct points in time. These geological records, preserved in rocks, serve as historical documents, allowing for the reconstruction of past magnetic fields. This understanding is crucial for deciphering the mechanisms behind the current drift. The study of volcanic activity contributes significantly to this exploration. When magma rises to the surface and solidifies, it retains the magnetic signature of the Earth's field at that moment. Analyzing these volcanic rocks reveals patterns of magnetic reversals and shifts, offering a timeline of geomagnetic activity. Additionally, sedimentary deposits also play a role, as they accumulate over millennia, encapsulating variations in the magnetic environment. Plate tectonics further influences magnetic field behavior. As tectonic plates shift and collide, they alter the distribution of geological features, affecting how the magnetic field interacts with the Earth's surface. This interplay can lead to localized anomalies, where the magnetic field may be significantly stronger or weaker. Understanding these geological processes is vital for predicting future changes in the magnetic field. The complexity of this system underscores the intricate connections between geological phenomena and magnetic field dynamics. Each discovery enriches the broader narrative of Earth's evolving nature. This evolving nature is intricately linked to the connection between magnetism and the electrical conductivity of rocks. Geological formations contain various minerals, each with unique properties that contribute to the planet's magnetic field. These minerals often exhibit ferromagnetic characteristics, meaning they can become magnetized in the presence of a magnetic field. When subjected to heat and pressure, certain rocks undergo changes that can enhance their conductivity, allowing them to respond more dynamically to external magnetic influences. The interplay between these two phenomena is particularly evident in volcanic and metamorphic rocks, where processes such as crystallization and recrystallization play critical roles. In regions of tectonic activity, the movement of magma can create localized variations in both magnetism and conductivity. These variations, in turn, inform scientists about the underlying geological processes, leading to a deeper understanding of mantle dynamics. Electrical currents generated within these conductive rocks can further influence the surrounding magnetic field. This feedback loop highlights the complexity of Earth's magnetic environment, illustrating how geological processes shape and are shaped by magnetism. The shifting poles, observed through satellite data, reflect these intricate connections, providing crucial insights into both the past and future of the planet's magnetic system. Such understanding not only uncovers the mysteries of Earth, but also informs predictions about changes yet to come. Human activity exerts subtle yet significant influences on Earth's magnetic field. Urbanization and industrialization contribute to the alteration of local magnetic properties, often masking the natural signals emitted by the planet. This region, densely populated with infrastructure, generates electromagnetic pollution, which can interfere with the sensitive instruments designed to measure geomagnetic changes. The extraction of natural resources also has implications. Mining operations disturb the geological substrates, affecting local magnetic anomalies. Such disturbances can alter the alignment of magnetic minerals, leading to localized fluctuations in magnetic strength. These variations are not merely academic. They hold practical importance for navigation systems reliant on stable magnetic references. In addition, the increasing number of satellites orbiting the planet contributes to our understanding of the magnetic field. These instruments collect data on fluctuations and anomalies, revealing the dynamic nature of Earth's magnetosphere. They document how human technology interacts with natural phenomena, providing insight into the broader effects of human presence in the atmosphere. Climate change, driven by human actions, indirectly impacts the magnetic field as well. Alterations in atmospheric conditions can influence electric currents in the ionosphere, which in turn affect magnetic measurements. This complex interplay highlights the need for continued research, ensuring that both natural and anthropogenic factors are carefully considered in understanding Earth's magnetic landscape. The historical context of magnetic field studies reveals a rich tapestry of exploration and discovery. The initial observations date back to ancient civilizations, where the properties of magnets were noted, often linked to navigation. Mariners relied on magnetic compasses, marking a pivotal moment in human history that extended travel and trade. By the 17th century, scholars began to investigate the Earth's magnetic properties more systematically. Pioneering figures like William Gilbert published foundational texts that described magnetic phenomena, laying the groundwork for future studies. The emergence of geomagnetic surveys in the 19th century further advanced the understanding of the magnetic field's structure and behavior. Expeditions charted magnetic declination and inclination, providing essential data for both scientific and navigational purposes. The advent of the 20th century introduced revolutionary technologies such as the magnetometer, allowing for more precise measurements. Research expanded to include the study of magnetic reversals and the geodynamo theory, which explained the generation of Earth's magnetic field through the movement of molten iron in the outer core. These investigations revealed that the magnetic field is not static, but subject to fluctuations and shifts over time. Acknowledging these changes has become crucial in understanding not only the Earth's past, but also its future, as it continues to drift and evolve in response to dynamic geophysical processes. This potential for utilizing magnetic field data opens new avenues for enhancing climate models. Magnetic field variations provide critical insights into the interaction between the Earth's core and its atmosphere, revealing patterns that can influence weather systems. By integrating this data, researchers can offer a more comprehensive understanding of climate dynamics, encompassing both surface conditions and deeper geophysical interactions. These shifts in the magnetic field are not merely isolated phenomena, they correlate with various atmospheric events. Anomalies in magnetic intensity often precede significant climatic changes, offering predictive capabilities that can improve weather forecasting. This relationship underscores the importance of continuous monitoring of the magnetic field, allowing scientists to observe long-term trends and short-term fluctuations. Data derived from satellite observations and ground-based measurements contribute to a more nuanced understanding of this region. The interplay between the magnetic field and climate systems can illuminate complex behaviors, such as the influence of solar activity on terrestrial weather patterns. This holistic approach may enhance the capacity to predict extreme weather events, aiding in disaster preparedness and response. Continued research into the Earth's magnetic field may also reveal historical climate transitions, providing invaluable context for current warming trends. Understanding these connections is essential for developing resilient strategies to address the challenges posed by a changing climate. Artificial intelligence plays a pivotal role in analyzing magnetic field data. Advanced algorithms can process vast quantities of information collected from satellites and ground-based observatories. By identifying patterns and anomalies, these systems enhance our understanding of the dynamics at play within the Earth's magnetic field. The intricate movements of the magnetic poles, influenced by variations in the molten iron flowing within the outer core, are now more accessible thanks to machine learning techniques. In this evolving landscape, AI systems can predict future shifts in magnetic orientation. They analyze historical data, allowing researchers to develop models that simulate potential scenarios. This capability contributes not only to understanding the past behavior of magnetic fields, but also to anticipating their future trajectories. Such predictive power is crucial for navigation systems, wildlife migration patterns, and even climate interactions. The integration of artificial intelligence into this field signifies a shift toward a more data-driven approach. Collaborations between physicists, geologists, and data scientists foster an environment where insights emerge from complex datasets. This synergy enables a more comprehensive examination of how magnetic fluctuations influence various Earth systems. As AI continues to evolve, its application in analyzing magnetic field data will likely open new frontiers in our understanding of planetary behavior and its implications for life on Earth. Public awareness about magnetic field issues plays a critical role in enhancing collective understanding of the Earth's geophysical dynamics. Knowledge of these phenomena is essential for recognizing their potential impacts on technology, navigation systems, and even climate patterns. Current shifts in the magnetic field, driven by processes within the Earth's core, can influence satellite operations, disrupt communication systems, and affect power grids. This region of scientific inquiry extends beyond mere academic interest. Individuals and communities benefit from awareness of magnetic fluctuations, particularly in areas prone to geomagnetic storms. These storms can induce currents that pose risks to infrastructure and pose challenges for emergency preparedness. Educational initiatives can foster a deeper grasp of these concepts, empowering communities to engage with the data and interpret its relevance to daily life. Increased public interest may also drive funding and research towards mitigating risks associated with magnetic field changes. Collaboration between scientists and educators ensures that the complexities of these natural phenomena are conveyed effectively. Outreach programs that highlight the role of the magnetic field in protecting Earth from solar radiation can inspire curiosity and a sense of stewardship. As understanding grows, so does the ability to appreciate the delicate balance of forces influencing life on this planet, emphasizing the interconnectivity of Earth's systems and the role of human agency in safeguarding its future. The future of Earth's magnetic field holds the potential for new discoveries that could deepen comprehension of geomagnetic phenomena. Fluctuations in polarity and the shifting magnetic North Pole present avenues for exploration into the underlying processes driving these changes. Monitoring these transitions enhances awareness of their broader implications for navigation systems, wildlife migration, and technological infrastructures. Research initiatives utilizing satellite observations and ground-based instruments are beginning to unveil the complexities of the magnetic field's behavior. These ongoing efforts provide insights into the dynamics of the outer core, where molten iron generates the magnetic field through convection currents. Understanding this geodynamo effect is crucial in unraveling the mysteries of the planet's interior. The potential for unforeseen discoveries extends into the realm of climate science. It is hypothesized that fluctuations in the magnetic field may influence atmospheric dynamics, potentially affecting weather patterns over extended periods. Such connections could reshape perspectives on climate variability and resilience. In addition, the exploration of past magnetic field reversals through geological records may yield clues about Earth's historical climate and environmental changes. This knowledge can inform predictions about future shifts, enhancing preparedness for the consequences of a changing magnetic landscape. The convergence of technology and scientific inquiry the ongoing mystery surrounding Earth's drifting poles invites continued investigation into its implications for our planet. Changes in magnetic polarity and the shifting magnetic field can influence various aspects of geological and atmospheric activity. This phenomenon affects navigation systems, animal migration patterns, and even the structure of the Earth's own magnetosphere. The dynamic nature of these shifts remains a subject of intense study, as researchers seek to understand the underlying processes driving such movements. Variations in the Earth's outer core, where molten iron generates magnetic fields, are believed to play a crucial role. These processes are not only essential for maintaining life on the surface, but also for protecting it from harmful solar radiations. The implications of this drift extend beyond immediate environmental effects. They may offer insights into the long-term stability of Earth's magnetic field, crucial for sustaining life. Observations suggest that the magnetic poles have moved significantly over geological time, with previous reversals occurring without catastrophic consequences. As scientists continue to analyze data from satellites and ground-based measurements, they remain poised to unlock the secrets of this enigmatic phenomenon. Understanding the mechanics of pole drift can enhance our knowledge of Earth's history and its future, revealing the intricate connections between the planet's magnetic field and the biosphere it sustains.